Section 2.3, Projectile Motion. I want to start our discussion of projectile motion by looking at this picture here. In this diagram, we have an object that is being dropped out of a window. So this is not projectile motion, this is free fall kinematics. If we observe a few characteristics of this object, we'll see that in this diagram, we've depicted the magnitude of the velocity of the object by vector diagrams, directed line segments. And you can see over time, as this object falls, its velocity is increasing. What's causing this object's velocity to increase is acceleration. And the acceleration is due to gravity. So gravity causes all objects that are falling downward towards the center of the Earth to accelerate at a rate of 9.8 meters per second squared down. So we have an initial velocity of 0. If we were to launch this ball from the window with a horizontal velocity, it would take a new path. And the new path that it would take is this red dashed line in this diagram. This trajectory, this pattern that some of you might even anticipate, is a pattern that is experienced by objects that are undergoing projectile motion. So let's take this moment to define what projectile motion is. Well, first of all, a projectile is any object that moves along a two-dimensional curved trajectory in response to gravity. And projectile motion is the motion of this projectile under gravity. The third definition here is the time of flight. This object spends some time in the air. So it's thrown out the window, it's either dropped or it's thrown horizontally. Either way, it's going to spend some time in the air. And the amount of time that it spends is called the time of flight. It's perhaps the most important quantity that you can determine in projectile motion. Once you find the time of flight, you can calculate everything. You'll have enough information to find everything. So it's really like a key to solving all possible projectile motion problems. So I want you to take note of the difference between an object that is free falling vertically, or an object that is undergoing projectile motion. And there's one thing they have in common. The first thing to observe is whether an object is dropped from a height or thrown vertically from a height, it falls at the same rate. So this object here, and any object in fact, whether you choose to drop it or throw it out with a horizontal velocity, is going to fall at the same rate and is subject to gravity. So gravity will cause it to accelerate downward. Now the difference between these two has to do with the fact that the projectile will cover a horizontal distance. And this horizontal distance, x for horizontal, is called the range. And it's received this horizontal distance because when it was launched out of the window, it was given an initial velocity, which is depicted as a blue vector. And this velocity is a horizontal velocity, so it's been given an initial x, or horizontal velocity. But I want you to make note of the magnitude of the horizontal velocity during the entire time of flight. What you notice about the magnitude of the horizontal velocity during the entire time of flight is that it's the same, it's constant. Its horizontal velocity is not changing. So for the entire time of flight, it will continue to move horizontally. The faster you throw it horizontally out the window, the greater this distance will be. The range will be. Question?
Is the amount of time it's going to take for the ball to hit the ground the same, like for the vertical fall as it is for projectile motion?
Yes. In fact, if an object is released from the same height, it'll take the same amount of time for these two objects to fall. And this next diagram here is a time-lapse photograph of just that. So a picture is taken every second, and these white lines across are intervals of time. And you can see that whether or not the object is dropped or thrown horizontally, it's going to travel downward at a rate of 9.8 meters per second squared down. When studying projectile motion, we make a few simplifications. And take a look at this little Cartesian plane that I've drawn. In order to save us some time when performing calculations, we're going to transfer or change all of our directions into either pluses or minuses. So we're going to assume that the right and up are positive, and the down and left are negative. So this is an assumption that we make. So we can write, to summarize, all motion to the right is positive. We therefore understand that left is negative. Therefore, we can state that all motion up is positive, and conversely, down is negative. So one of the techniques that we'll be using in solving projectile motion problems is to work with motion in only one direction, either horizontal or vertical at a time. By doing so, we will use information provided about the motion in one direction to solve for a time value. And as I said before, this is key. Solving for time is unlocking the key to all values in projectile motion. And it links the two frames of reference, horizontal and vertical, together. Though the projectile behaves independently in its vertical motion as it does in its horizontal motion, they're linked by the time that they are in the air. In general, we're going to look at three types of motion. The first type looks like this. Where an object is thrown horizontally from a height above the ground. We'll call this type 1. In type 2, the object is launched at an angle from the ground. Imagine the trajectory that this projectile will travel. If you've played Angry Birds, you might guess that the projectile trajectory would look like this. A symmetrical parabola, where the object is launched at an angle from the ground and returns back down to the ground. This is type 2. The third type is slightly more complicated and is almost a combination of the two of them. Type 3 would be when an object is thrown at an angle but from a height above the ground. So the path that this takes is a bit more complicated. For part of its trip, it has a symmetrical component, a symmetrical parabolic component, but this object continues to fall past that. And this is type 3. You'll see that each of the possible questions falls into one of these categories. And to solve them requires different equations and different math. But once you've solved one of each of the types, you'll be presented with all the possible mathematical opportunities or situations, and therefore be able to expect what to see when solving any other problem. Let's take a look at the first example. A beanbag is thrown from a window that is 10 meters above the ground with an initial horizontal velocity of 3 meters per second. Part A, how long will it take the beanbag to reach the ground? That is, what is its time of flight? And part B, how far will the beanbag travel horizontally? That is, what is its range? Before starting any projectile motion question, before attempting to decide what type it is, type 1, type 2, or type 3, the very first step is to determine the initial x and y components of its velocity. In this question, it tells us that the object is launched with an initial horizontal velocity of 3 meters per second. Since it is thrown to the right, I'm going to indicate that with a plus sign. So the plus means right. If an object is launched horizontally, then it has no vertical component to its velocity. So v1y is 0. Whenever you add the letters x and y beside a symbol, you're giving it a direction. So the x implies that it's horizontal. So there's no need to put an arrowhead on top of this v or on top of this v, because the little x denotes the direction and reminds you that this is a vector. So this is the first step. Determine the initial x and y velocities. Now let's attempt to answer the question. Part A. Determine the time of flight. When an object is falling from a height above the ground, the time it spends in the air depends on one single factor: gravity. Gravity causes it to fall, and gravity always acts in the vertical direction. So when you're thinking of time of flight, you always have to think of the vertical direction, or the y direction. So what we have to do is collect all the information we know about the y component of this object. So we've just determined above that the initial y velocity is 0. We also know that in the y direction, acceleration is caused by gravity. And the acceleration rate is 9.8 meters per second squared. Instead of writing down, we're going to use a negative sign in front of it. We also know from this question, if you take a look at the diagram, that this object undergoes a displacement in the y direction of 10 meters down. So we'll write delta d y equals 10.0 meters. And please remember that since this is down, you need a negative. So that's all we know about the y direction, and what we want to find is delta t. Once you've established this, the rest is kinematics. It's no longer projectile motion. You look at the variables that are given, and you find an equation that includes everything that's given and required. So for this, we can use equation number 3, which says delta d is equal to v1 delta t plus 1/2 a delta t squared. Now if you notice, I took away the arrowheads and I put in little subscripts for y. It reminds us that we're only allowed to use y variables here, or information collected about the vertical component of this object's motion. If you want to solve this for time, you should be cautious. There is the letter t in 2 spots, delta t and delta t squared. So this is actually a quadratic equation. And in order to solve a quadratic equation, you'll need the quadratic formula, unless there's something that allows us to simplify it. Since we've stated that v1y is 0, this term is canceled out. And we've seen this situation before in kinematics. So this equation simplifies to delta dy equals 1/2 ay delta t squared. And we're familiar with rearranging this equation, so we can do it quickly. Delta t is equal to the square root of 2 delta d over a. And we're ready to sub and solve. When you do, please use plus or minus to indicate the direction. So this becomes the square root Punch it into your calculator and tell me the answer to two significant digits. You get 1.4 seconds. Anytime there's a type 1, you'll get this situation happening where you cancel out v1y delta t because v1y is 0. So this is a bit of a trick for all type 1s. And what we've done is we've found the time of flight. This is huge. This is the most important piece of information, and it unlocks the ability to answer any other problem, including Part B, where Part B wants us to find the horizontal displacement. Horizontal displacement in projectile motion is referred to as the range. When we're talking about horizontal displacement, we're obviously looking in the horizontal direction, or the x direction. So when answering questions about horizontal motion, you can only collect horizontal information. So from the beginning, we said that our initial horizontal velocity is 3 meters per second, and it's a plus 3 meters per second because it's to the right. We've said that the time of flight can be used for both x and y directions. So the time of flight is known. It's 1.4 seconds. And they want us to find the range, delta dx. So we need an equation that incorporates all three of these variables. The equation that we're going to use is the equation for velocity. And this equation states velocity is equal to displacement over time. We can rearrange this for displacement, and we get displacement is equal to velocity times time. This becomes, for all projectile motion questions, the equation for range. So every single question that asks you for the range, you're going to use this equation. It's really not much of a unique equation, it's just the equation for velocity rearranged. Nothing special. So let's sub and solve, and let's find the horizontal displacement or range of this projectile. Plus 3.0 meters per second for 1.4 seconds. If we put it in our calculators to two significant digits, we end up with 4 plus 4.2 meters. Now, when reporting your answer, state the direction. So the range is 4.2 meters. I've taken away the positive sign, and I'm going to put in right, because we've stated that positive is right. There's a type 1. Sample problem number 2. We have a soccer player running on a level field, kicks a soccer ball with a velocity of 9.4 meters per second at an angle of 40 degrees above the horizontal. Determine the soccer ball's time of flight, range, and maximum height. So just like the previous example, and what I want you to do for every single projectile motion question is determine the x and y components of its velocity. So let's take a look at its initial velocity. So this object, the soccer ball, was given a velocity of 9.4 meters per second at an angle of 40 degrees to the horizontal. In section 2.2, we learned how to break up a vector into its x and y components. So if we look at this vector here, 9.4 meters per second has this as its x component, which we'll call Vix, and this vector as its y component, which we'll call Viy. So we have to find Vix and Viy using the diagram and trig ratios to solve this. So let's start with the x component of the initial velocity. The x component is the adjacent line with respect to the angle and the hypotenuse, 9.4. So adjacent hypotenuse is the relationship that exists with the cosine ratio. So Vix is going to be equal to 9.4 cos 40 degrees. If you punch this into your calculator, you end up with 7.2 meters per second. The direction of this x component is to the right, so we put a plus sign. Let's find the y component. The initial y component of this object's velocity is not 0 as it was in the type 1. It now has some initial upward velocity. The y component represents the opposite to the angle and the hypotenuse. Opposite hypotenuse leads us to sine. So we have 9.4 sine 40 degrees. Punch it into your calculator, into two significant digits. You get 6 meters per second up, and up is denoted with a plus sign. So we haven't even attempted to answer the question yet, but now we can, because we've completed and determined the x and y components of the initial velocity. Part A, determine the time of flight of this object. When we talk time of flight, we are talking about the vertical component, as time of flight is governed by gravity in the y direction. So we need to collect all information we have about the y direction. We've just calculated our initial y velocity as plus 6 meters per second. We know our acceleration in the y direction is negative 9.8 meters per second squared. And there's another piece of information. I want you to look at the vertical displacement of this soccer ball. So this soccer ball travels up in the air to a certain height, then back down. So what's its change in height at the end of its trip? 0. This object, because it returns back down to the same height, its vertical displacement is 0. And this is an important piece of information that you'll see in type 2 problems. So I've pointed it out to you, but you will be responsible to write that down whenever you see an object that starts on the ground and ends up on the ground. So remember that they want us to find time. We need an equation that incorporates V1, A, delta D, and delta T. We end up using the same equation as we did equation number 3. It says delta D is equal to V1 delta T plus 1/2 A delta T squared. And we're going to solve this for delta T. And we hesitate a bit because delta T appears twice. And in the previous example, V1 was 0, so it allowed us to simplify this. But in this case, V1 is not 0. There is, however, one thing we can do. We know that delta dy is 0. So we'll rewrite this as 0 equals v1y delta t plus 1/2 a delta t squared. And I'm about to show you how to solve this for delta t. It's a bit of a trick. It might not be intuitive, but after seeing me do it and practicing this several times, it should become automatic for you. we have delta t in two terms, which poses a bit of a situation. What I want us to do first is take this v1 delta t and bring it over the equal sign. If we do, what will happen to its sign? It becomes negative. So we'll rewrite this as negative v1y delta t is equal to 1/2 ay delta t squared. Now here's where the math skills come in. On the left side, we have a delta t in every single term on the left side. And we also have a delta t in every single term on the right side. So we can actually divide both sides by delta t. And what we're doing essentially is reducing this expression, just like you would reduce fractions. We're not changing the value or the meaning, we're just reducing it. If we do so, the delta t's on the left side will cancel out, and the delta t's on the right side will be reduced. So we'll write ourselves a reminder that we divide both sides by delta t, and you'll see this in all type 2. If we do this, this equation simplifies to negative v1y is equal to 1/2 ay delta t. Now let's solve this for delta t. Delta t is equal to negative 2 v1y over ay. And we can sub and solve here. Make sure you include your direction. We have negative 2 times an initial upward velocity of plus 6 divided by an acceleration of negative 9.8 meters per second squared. If you punch this into your calculator and report your answer to 2 significant digits, you get 1.2 seconds. Your answer should be positive. We cannot accept a negative value for time. It's invalid. So we found our time of flight, and this is the most important thing. The rest is easy. So the time of flight is 1.2 seconds. With this time of flight, we can do things like answer part B, determine the range. And remember that the range is the horizontal or x direction. So we just calculated the time. It's 1.2 seconds, the time of flight, the time the soccer ball is in the air for. We know our initial x component of its velocity from the example is positive 7.2 meters per second. And we want to find delta dx, the range. We're going to use the equation we did in type 1, which is the range equation. So we sub and solve, and we get plus 7.2 meters per second times 1.2 seconds. To 2 significant digits, we get a range or horizontal displacement of 8.6 meters. When you state your answer, make sure you replace the plus or minus with the appropriate direction. The range of the soccer ball is 8.6 meters right. Let's finish this up and do part C. In part C, they want us to find the maximum height. It's important to note what direction we'd be using, vertical or horizontal. Heights, vertical, so we'll be using all information in the vertical direction, or y direction. So remember, the object takes this path, goes up to maximum height, and then falls back down. What do we know about maximum height? What do we know about max height from free fall kinematics? The velocity at max height is 0. So we're going to take a look at this information. We know that this object had an initial vertical velocity of plus 6 meters per second, and when it reaches max height, its velocity is 0. The acceleration in the y direction, because it's under the influence of gravity vertically, is negative 9.8 meters per second squared. And we want to find its maximum height, its displacement in the y direction. So we need an equation that uses v1, v2, a, and delta d. Now, can we use the time of flight that we calculated? Well, we're not looking at the time it takes to go up and down. We're looking at the time it takes to go up. So we don't have the time it takes to go to maximum height. So let's try to use an equation that doesn't have time in it. We're therefore limited to equation number 4. And equation number 4 states v2 squared equals v1 squared plus 2a delta d. And if we rearrange this, delta d is equal to v2 squared minus v1 squared over 2a. Let's sub and solve. If we substitute, we get 0 minus plus 6 meters per second squared. And keep in mind that the negative sign is in front of the plus 6, outside of the bracket. So when you square the 6, that negative will remain. And it's important to do so because otherwise your direction will be off. Divided by 2 times negative 9.8 meters per second squared. You punch this into your calculator, what do we get? 2 sig digs. To 2 significant digits, the answer is 1.8 meters. And it should be positive. And that makes sense because the maximum height should be up, not down. So we can state the maximum height is 1.8 meters up. Now I want you to take a look at this diagram again. I told you that we didn't have information about the time and maximum height. We know that the time for this entire duration is 1.2 seconds. But a type 2 projectile motion question is perfectly symmetrical. So you can actually state that the time it takes to reach max height would be equal to 1.2 seconds divided by 2. And you could have used that additional piece of information. Now this is only the case in a type 2 example in which you've created a perfectly symmetrical parabola for the trajectory of the projectile. Keep that in mind. Now you might not need it or use it, just like we didn't use it, to solve for the maximum height, but it'll help complete your understanding of projectile motion. For homework after this section, I want you to complete all of the questions that are either type 1 or type 2. In the next lesson, we'll be learning the third type, an object that is released at an angle from a height above the ground. Good luck.